In this video, I'm going to show you guys how to run regression, correlation, and analysis of variance using the stats tools in Excel. So what I've pulled up is Dr. Dean's bivariate stats Excel file, which you can find on Learning Suite on the day for the Midterm 2 exam. And right now I'm looking at the page for knee repairs. So what we're going to do first is the analysis of variance, or ANOVA. And remember that all an analysis of variance tells us is whether or not there is a significant difference between treatments. So for example, here we have the load at failure for 3 different types of knee replacement treatments. So vertical suture, meniscus arrow, and fast T-fix. So we have the load at failure for each of these types, and they're by column. Here's the box plots, and here is the ANOVA already run. But we're going to run it again. Okay, so let's go over to the Data tab and do Data Analysis. We're going to select Single Factor ANOVA. Hit OK. Okay, so it asks us for our input range. So we're going to just choose all of the data that we have for each of the treatments. On single factor, that just means we're only concerned with the load at failure. So that's the factor we're concerned with. Our data is grouped by columns, so we'll leave that there. We did not put the labels in the first row, so we can leave this unchecked. And we'll also leave the alpha level at 0.05, meaning that we're testing to see significance at that level. And let's go ahead and send the results to a new worksheet. I'm going to call it ANOVA. Okay, let's hit OK. All right, so we get a new sheet called ANOVA. If we expand this, we can see some different information. The main question is whether or not there is a difference between each type of treatment for the factor that we're concerned with. So for the load at failure, is there a difference between these 3 treatments? So if we take a look at the p-value for between groups, we see that it is quite low. It is less than 0.05, so we can conclude that there is a statistically significant difference between or among the treatments. We don't know which 2 or which 3 are different. All it takes is just 2 being different in order to trigger this. So that's the sort of information that we get from conducting an analysis of variance. And that's the sort of thing that you'll see on the exam. Okay, next let's run a regression. So I'm going to go over here to Height and Self-Esteem tab, scroll up to get the data. So this is just a simple regression. We only have one independent variable, height, that leads us to the dependent variable of self-esteem. We want to know if there's a correlation between height and self-esteem. So we will first conduct a regression and then we will look at a correlation matrix. So let's go back over to Data Analysis and scroll down to Regression. Hit OK. Alright, so our input Y range, that's our dependent variable. In this case, that's self-esteem. So let's highlight that. Our input X range, so if we had more than one independent variable, we would simply highlight all of those. But in this case, we only have one independent variable of height. So we'll just highlight that. We can leave the confidence level at 95%. And we don't need any of this other information right now, so let's just put this in a new worksheet. I'm going to call it Regression. And hit OK. Before I hit OK, I just want to make one note that In examples that we've had, the dependent variable has always been all the way on the right. This might not always be the case, so please read the problems that you get very carefully in order to make sure that you're selecting the correct column as the dependent variable. Okay, so we have our output in a new sheet. We can see our R squared and the adjusted R squared. And we also have, let me expand this a little bit more, our coefficients and our p-value. So in this case, we're not looking at the intercept, we're just taking a look at the independent variable of, in this case for us, it's height. And we take a look and ask ourselves, is the p-value for height less than 0.05? In this case it is. So we can conclude that there is a statistically significant relationship between height and self-esteem. And if we look at our correlation matrix that we'll make, we can see just for how many units in height that we accumulate, how much self-esteem that we get. So right now we understand that there is a relationship. Let's go ahead and go back to the height and self-esteem tab to run the correlation matrix. Let's go back to data analysis. I'm going to scroll up to correlation, hit OK. So the input range, again, if you have multiple X or independent variables, you're going to highlight all of those. In this case, I'm just going to highlight height and self-esteem. So we want to know if there's a correlation between those two. It's grouped by columns again. We did not put labels in the first row. And let's put this in a new worksheet. I'm going to call it correlation. Hit OK. And so this is a very simple correlation table because we only have the one independent variable. If we take a look, this is our R value, or Pearson correlation coefficient. It has a value of 0.73. So we can conclude that there is a moderately high or high positive correlation between height and self-esteem. And for each unit of, or for each inch that we add in height, we get 0.73 units of self-esteem. Okay, so remember we'll need ANOVA, or analysis of variance, regression, and correlation. I hope this helps, and good luck to you.